Welcome back, physics fans, and we're starting on part two of the electrostatics lesson. And this is where we actually start talking about the electrostatics, except for the mentioning of the formula. The last lesson was just understanding gravity so that we can come on over into this chapter and understand Coulombs Law and all of electrostatics a lot easier because of how analogous it is to gravity. Matter is made up of electrons and protons and neutrons. And we put electrons, neutrons, and protons together. They're called atoms. And an atom has a nucleus, and it has electrons going around in shells, if you wanted to use Bohr model and stuff like that. And when atoms bond together to form solids, the electrons can be A, tightly bound together in the atoms, like in covalent solids like glass, and these materials are called insulators. Or when we covalently bond them together in metals, the electrons can go from one orbit to the next orbit to the next orbit of adjacent, popping out the next electron out to the next electron, from valence shell to valence shell to valence shell. And there might be a little bit of resistance from doing that, hence the resistance in wires. But the electrons can bounce from atom to atom to atom to atom, and that's what makes up a conductor. So there's insulators versus conductors. Now, whoops, not too fast, here we go. The subatomic particles like protons, electrons, and neutrons, they make up everything, by the way, have a property known as charge. You probably already knew it, but all you had to do is ever recite it, never could use it. Today we'll be using it. And it is this charge that is responsible for electricity. And my guess is you didn't know that these charges are also responsible for magnetism. Sorry. There are two facts about charge that we need to know. Three facts. Okay? Charge. There's two types of charges. We'll call them negative and positive. And that's a pretty good way that Benjamin Franklin came up with it because they do add mathematically, and negative and positive make sense. He could have called them white and black or east and west. Charge is a measurement, is measured in the units of, what's the units for a charge? Anyone know? Coulomb. And the letter that it's abbreviated to, capital C. So we could have 5 coulombs of charge. Okay, like we could have said mass and kilograms. What is the unit of mass? It's kilograms. Kilograms, and abbreviated to kg. Anyways, erasing that. We're not talking about gravity right now. You could leave it on your sheet though. Another important fact about charge is that it's quantized. Here's a word, which is why the variable makes sense. What variable? Well, what's the variable for charge? Q. It could also be capital Q. Just like the variable for mass was usually a small m, but you know, in that GMM over R squared, sometimes I did m of the planet and made it big. So quantized. And that simply means it's kind of like money. What does that mean? Okay, there is a smallest unit in money, and that's called the cent. Now, on paper, you could have a half a cent, but in your pocket, you can't have a half a cent. How much money is in your pocket? Ah, 32 cents. You can't say 32.2 cents. Why? Because it comes in a lowest particle, lowest, smallest value, a penny. Now, it's really hard to get pennies nowadays, practically impossible. So you might have to go in nickels. But you can understand that it's quantized. We can't break it down, and we never can have a fraction of a penny in our pocket. Well, the same thing is with charge. There is a smallest unit of charge, and that's called the elementary charge. The elementary charge, and it's also sometimes referred to as the fundamental charge. And this is the charge that is on a proton and is on the electron. And that value is 1.6 times 10 to the negative 19th coulombs. And it's given a little symbol as E for elementary charge. It would be nice if it was just 1 coulomb, because then if I said, oh, this object has 3.2 coulombs, you'd go, liar. It only comes in whole numbers of, but they don't. But they do come in whole numbers of E charges. So we can have 1 elementary charge. We can have 2 elementary charges. We can have 3 elementary charges. We can have 4 elementary charges. But we can't have like 4.2 elementary charges. That just does not exist. That does not exist in nature. So that means if the smallest charge that is available is 1.6 times 10 to the negative 19th, and that's not an if, that is the truth, what's the next smallest charge that is possible? That would be 3.2 times 10 to the negative 19th coulombs. And the next possible charge is 4.8 times 10 to the negative 19th coulombs. Why? Because that's 1e. This is equal to 2e. This is equal to 3e. 3 times the elementary charge, 4 times the elementary charge. So the next one here is 6.4 times 10 to the negative 19th coulombs. Now, you may not understand it fully right now, but if I tell you that there's an object that has a charge of 5.5 times 10 to the negative 19th coulombs on it, you would go, well, Mr. Curl, that could be on paper, but realistically, that never can exist in the universe. It can't, because it has to be in numbers of elementary charges. We also are seeing this. How often do we have to look at this? Not very often. It's like, did you know mass is quantized? No. Well, it is. How so, Mr. Curl? Okay. The mass of a proton is 1.67 times 10 to the negative 27 kilograms. The mass of an electron is 9.11 times 10 to the negative 31st kilograms. Now you might have gone, okay, I understand that. But then I go and shatter your understanding until you correct me because I'm wrong. I have a molecule, just one molecule, and its mass of this molecule is 5 times 10 to the negative 35 kilograms. It's a really small molecule. That's not possible. You cannot make a molecule in this universe with that mass. Why? It's smaller than the quantized value of mass. The quantized value of mass is 1 proton. You can't have a half a proton. You can have a hydrogen atom. That's the smallest molecule you can have. You can't have a half a hydrogen molecule. So the mass that I just wrote down here of 5 times 10 to the negative 35 kilograms, it can be on paper. It never exists. It can't even take an electron and chop it in half. You can't. So you can have something that has a mass of 18.22 times 10 to the negative 31st kilograms. It'd be 2 electrons. 18.22 would be 2 electrons. But you couldn't have a mass of 4.11 times 10 to the negative 31st. That's about a half an electron. You can't have something that has mass of half an electron. Why? Because the electron is the smallest. The proton is the smallest of the protons. It doesn't have anything else. That's quantization. Turn on over. The charge on a proton is E. What is the charge on an electron? Anyone want to raise a hand and yell it out after I point to them? What's the charge on an electron? No one want to hazard a guess and be wrong? Okay, YouTube fans, just tell me. Oh, I hear someone on the YouTube. There we go. They said negative E. That's correct. It's the same charge as a proton, but negative. So an electron has a negative elementary charge. So the smallest unit is elementary charge. And any larger amount is n times that elementary charge, where n is an integer. So n is 1, 2, 3, 4, all the way up to as big as you want. Let's learn some atomic data right now. You probably have all these numbers memorized, I'm pretty sure. What is the charge on an electron? It's negative 1.6 times 10 to the negative 19th coulombs, or you could just write down negative E. What's the charge on a proton? That would be positive 1.6 times 10 to the negative 19th coulombs, or just E. What's the charge on a neutron? Thank you. Perfect answer, 0. What's the symbol? Let's write these symbols down for you. We write down E negative now. We write down P positive, and we write down N neutral with 0. We write the charges to the top right of them. What's the mass of an electron? See if you remember that from what I had up on the screen. 9.11 times 10 to the negative 31st kilograms. What's the mass of a proton? 1.67 times 10 to the negative 27th kilograms. What's the mass of a neutron? Hmm? You'd think that it's the same as a proton. It's not. Yes? 1.68 times 10 to the negative 27th. Just a little bit heavier than a proton. How much more heavier than a proton? An electron. If we physically take a proton and electron and put them in the same space, we get a neutron. That's a fact. You learned this in Science 10. What was it called? Beta decay in radiation. And that was a neutron in your nucleus changing to a proton and spitting out an electron flying out. See, you ended up with a proton and an electron when beforehand you only had a neutron. Does it also make sense in charge? If I pushed an electron and a proton together into the same spot, will the charge balance out? Yes, because a negative charge and a positive charge becomes a zero charge. Now, that might make you think that inside a neutron, things are not neutral. And that's correct. But the total charge on a neutron will be zero because it'll have a positive charge and a negative charge inside. Coulombs Law, K, Q. I'll just do two different Q's all over R squared. And remember, we need a constant, and that's our K. So F is the electrostatic force, also referred to as the Coulomb Law force. And what unit is it going to be measured in? I'm sure you can help me with that. Thank you for helping me. I had to wait for this person on the internet actually answering it because it's measured in newtons. All forces are measured in newtons. K is the electrostatic constant. And its value is 9 times 10 to the ninth. Its units are weird. I'm only going to write down the units for it maybe this one time, maybe not, maybe a couple more times. It's newtons times meters squared divided by coulombs squared. Q1 and Q2 are both charges, and they're both magnitudes of these charges. They're magnitudes. and they're measured in coulombs and abbreviated with a C, and R is the separation distance. Of Q1 and Q2, and that is measured in meters. There's one more aspect of Coulombs Law, and that is like charges repel and unlike charges attract. And I call this logic, and this gives us our direction. Okay. Previously in physics, when we had a negative force, what did that represent? What did the negative mean? Opposite direction. Very good. We're not going to worry about negatives in Coulomb's law. Why? No. Forces do have direction, but we figure out direction by this logic. We figure out the direction by looking at the signs of the charges that we're putting into the formula. So if in our calculations of KQQ over R squared, we get a negative, ignore it. Who cares? Because the negative only told us the direction, and that's not how we're doing it anymore. We're figuring out the direction by logic. We're not figuring out the direction by a negative. So that means when you put the electron charge into Coulomb's law, you don't have to put a negative. Because the negative is just going to help us with direction, but we already know which direction it's going to go. So if you put electron as positive 1.6 instead of negative 1.6 times 10 to the negative 19th, you going to get the wrong answer? No, you'll still get the right answer because you're going to ignore all signs. Because the sign only tells us the direction, and we use a different method to get the direction. Is this going to be the case always in physics? No. This is how we do it in physics 12 because it's easy and it's always right. Okay? So you never use signs in your calculation. If you do, will it be wrong? No, because you will all feel very comfortable in telling me the direction it is by using logic, not by using the signs. So this is how you solve a problem. Boom. You express charges in coulombs. What do you mean by that? Well, sometimes there could be millicoulombs, like 5 millicoulombs. It could also be 3 microcoulombs. So you can't throw that into the formula. 3 microcoulombs is 3 times 10 to the negative 6 coulombs. So you have to get rid of the metric prefixes. And we get a lot of metric prefixes here. Why do we get a lot of metric prefixes? Because stupidly or weirdly, a coulomb is huge. So if we're actually going to deal with real life charges, we won't be dealing with coulombs. We'll be dealing with millicoulombs, microcoulombs, nanocoulombs. So you have to change it into scientific notation. You have to substitute the charges into the formula and solve. And then you find the direction by looking at the charges that you put in And if they're the same charge, you now know they're repelling. And if they're unlike charges, they're attracting. Just for the heads up, those people that are going into university are going to see this again. The Coulombs law is actually written this way without using this logic. It's going to be negative K Q over R squared. Why negative? Because when we have two charges, here's Q1 and Q2, and let's both make them positive. This is our vector towards the other object, but they're going to repel. So this is the vector of the force. This is the force, and this is the R. And they're going to be in opposite directions. So that's why there's a negative there. If this is positive and that's positive, we get a negative. So sometimes you'll see the equation with a negative in it. Don't worry about it. That's just beyond physics 12 right now because we already know which direction things are going. Logical. Here's how to solve a question. It's already on the page for you, already solved. Determine the magnitude and direction of the electrostatic force on an electron of a hydrogen atom that's exerted by the proton that's in the nucleus of the atom. Assume the difference of the distance of revolution, the distance of the orbit, the radius of the orbit is 0.53 times 10 to the negative 10th meters. That's about the radius of a hydrogen atom, by the way. So we use Coulombs law, KQQ over R squared. We use R as this number. And the charges, KQ, the QQ, are both 1.6 times 10 to the negative 19th. Then I get John going, hey, Mr. Curl, electron's negative, proton's positive. So I have to put one as negative, one as positive. And I'll say, nah, you don't. Put them both as positive. If you want to put negative, go ahead. Please do. It might help you out. But the negative positives are only going to tell us the direction, and we already know the direction. It's an attraction force. We already know that before we even put them in there. Because one's positive, one's negative, we know it's an attraction force. We know the direction. So you plug in the values, 9 times 10 to the ninth, one charge, the other charge, and how far apart they are. Mr. Calculator tells us that it's 8.2 times 10 to the negative 8 newtons. Okay? So that's the proton, that's the electron, and there's a force pulling it in. Nice, eh? So I would like you to try this one now. It's find the force on an electron that's in a helium ion. Now, what's this helium ion? Okay, let's go back to chemistry 9. A helium ion. Helium, first of all, has two protons and two neutrons. And it's an ion, so it only has one electron. So that's the nucleus. What's the charge on the nucleus? Two elementary charges, right? Find the force. Okay? I'm going to pause this, and the answer will pop up in 3 seconds. 1, 2, and there we go. As I said, folks, it only took you 3 seconds, and we got the answer, the electrostatic force. That's the attraction force that this electron feels towards the nucleus is that. Why do I have 3.2? Because it's two elementary charges. Why is it two elementary charges? Because there's two protons in the nucleus. Okay, and now if that's going to be the case, part B, what is the centripetal force? What would its velocity be? Well, and there's the answer for B, folks. Just already solved out for you. Hopefully I didn't surprise you with it popping up like that. So that's how fast an electron is going around in a helium atom, following the Bohr's model, helium ion. How fast is that? 5 million meters per second? That's pretty fast. In fact, that's getting close to about 2% the speed of light. So it's very relativistic. Last but not least, let's take a look at example number 4. Find the net electric force on object C. So I want to find out what the net force is on C. C is 3 microcoulombs. This is for homework. 3 microcoulombs. A is this, B is this. Pay attention. C is going to be attracted to A, so it's going to be a force this way. C is going to be repelled from B, so it's going to be a force that way. You have to calculate these two forces and add them up. And you can pack up, but this is how you would do it. K, Q, Q over R squared. That would be 9 times 10 to the ninth. Negative 2 times 10 to the negative 6. That's that charge. 3 times 10 to the negative 6. That would be that charge over the separation of 0.3 meters squared. And that'll get you the magnitude of that force. You have to use direction logic to get the direction of that. Which force am I talking about? That one. You have to do it again for the other one and then add them up. Try for homework. Thank you very much. Subscribe. Pound that like button. Subscribe often. Leave 8 comments, please. Every person leave 8 comments. I want to get onto that algorithm. I want to be #1 in Dover Physics Productions. In the content where Mr. Beast and Mr. Curl neck and neck. Oh, collab. Hey, Mr. Beast, I dare you to come visit me.